Okay, welcome to the NUPOC video study guide number 38. Let's look at the first question in the calculus section of guide 1. The first set of, I believe, 15 or 16 or so questions in this section focus on differential calculus, and then the rest we'll get to will be integral calculus. So this first question just asks us for a brief description of the differential and the derivative, and then a little bit about the first and second derivative. So a differential, let's do this one first. So a differential, let's bring it over here, right? That's just, they say in the solution manual, that's, they call that an incremental value of an independent variable. A good way to think about it, though, is a differential is just a small unit of, maybe length or area or volume or time or volume or time. It's just some dimension. It's just a very small, infinitesimally small value of some dimension, right? Some dimension. Okay, so if we had, for example, if we had just some function like this, right? Some random function, whatever. So we would have our differential length on this, right? So this, we would call this, if this is x and this is y, right? This would be our delta x, right? So this would be x1 and x2, right? So our differential length, dl, let's call it, would be, or we could call it dx, doesn't matter. Just put that here, dx, dl, is going to equal the limit as x2 goes to x1 of x2 minus x1, right? So dx is the limit as delta x gets very small as x1 and x2 approach each other, and we take the difference between them, right? And same thing if we're looking at a differential volume or differential area or differential time or something like that. It's just it's an infinitesimally small unit of some dimension, right? So what about a derivative, right? Let's look at this over here, right? So a derivative is the result, right? The derivative is the resulting, let's say, function after applying a differential operator, right? And a differential operator is something that we form with the differential. So the differential operator is, ddx or ddt or ddv or something like that, right? So after we apply one of these differential operators, which makes use of the differential that we just talked about in the first little part here, right? Then we get our derivative, right? So an example would be if we have x squared, right? That's our original function. Then we apply the operator ddx, right? Then we'll get 2x, and so 2x is our derivative, right? The resulting function after applying a differential operator ddx. So what about the first derivative? Let's just write it down here, right? First derivative. Well, that just tells us about the instantaneous. Well, can be used to find the instantaneous rate of change of a function. So we can evaluate it at a point, find the rate of change at a function at a very specific point, and the first derivative as a function just tells us how that how the slope of that function is changing for various values of the independent variable. So various values of time. As time goes on, how is the slope of the function changing? And then we can evaluate it at a particular time, let's say, and find what the instantaneous rate of change is of the function, or the tangent line to the function is another way to say it, right? So again, if this is our function, let's say right here, right, we can look, over the domain of the function, we can say, it increases and then hit some sort of maxima, and that's decreasing again. Or we could say at an instantaneous point, say right here, it'll tell us the instantaneous rate of change of the function, which is just the tangent line to that function there, right? Or the slope of that tangent line. Now the second derivative, right? This tells us about rate of change of the instantaneous rate of change. So it's the rate of change of the slope. That's a good way to think about it. And in terms of functions that are in terms of in terms of position and time, so position over time or something like that, we would have our first derivative would give us, say, velocity, right? That's just dx dt, right? Position over time. And our second derivative gives us rate of change of slope, or rate of change of velocity, whatever. So this would be, for example, again, if we're looking at position per unit time, this would be like d2x dt squared, right? So this would be acceleration right? And then we could take a third derivative and we could look at the rate of change of the slope, and on and on and on. Okay? So I think that's a pretty decent discussion. It covers most of the points that you'll find in the solution. Again, differential is just a infinitesimally small unit of some dimension, which gives us a differential operator, helps us form a differential operator that we can then apply to functions to find that derivative. And our first derivative talks to us about the rate of change of a function, gives us the instantaneous rate of change at a particular point on that function, which is the slope of the tangent line at that point. Our second derivative talks to us about the rate of change of the slope, tells us, again, if we're talking about velocity and acceleration, tells us is something speeding up, is it slowing down, is the slope increasing or decreasing. And we can also use these to test, I'm sure as you've seen already, maxima and minima and curvature. We can look by evaluating the function around these points where, say, the first derivative is 0 or the second derivative is 0, right? So if the first derivative is 0, it tells us we have 0 slope and the curve is flat, and all those great things. So it's really useful. So that's it, just a quick overview of differential, derivative, and the first and second derivative.